In this second section, I will explain my recent result on the Hamiltonian stability and the Hamiltonian volume minimizing property of Lagrangian theory in the complex hyperbolic space. Many examples of compact homogeneous Lagrangian sum-manifold in CN are known. Moreover, the Hamiltonian stability and HVM property of some examples are also investigated. For example, MGO proves that the standard torus in the complex Euclidean space is Hamiltonian stable, and it was conjectured that they are all Hamiltonian volume minimizing. However, Ili and Ono prove that almost all Lagrangian standard tori in CN are not Hamiltonian volume minimizing when the dimension is greater than or equal to 3. Besides the torus orbit, we know some good examples of Lagrangian sum-manifold which are Hamiltonian stable. For example, Amarze Onita proves that any parallel Lagrangian sum-manifold in CN is Hamiltonian stable. Here, parallel means that the second fundamental form of the Lagrangian sum-manifold is parallel. By the previous argument given in the first video, Lagrangian sum-manifold in CHN correspond to these examples via the canonical simple morphism phi between CHN and the CN are also Hamilton minimal in CHN. So it is natural to ask the Hamiltonian stability and HBM property of these examples in CHN with respect to the hyperbolic metric. Recently, I focused on the Lagrangian torus and investigated the Hamiltonian stability and HBM property of this Lagrangian torus in CHN. This is the result in the complex hyperbolic space. And compared with the case in complex Euclidean space, the result in CHN is somehow complicated. However, we can prove that if n is smaller than or equal to 2, any torus orbit in CHN is Hamiltonian stable and rigid. Here, rigid means that the null space of the second variation under the Hamiltonian deformation is found by trivial deformation, that is obtained by holomorphic Killing vector fields of the ambient manifold. And second, if n is greater than or equal to 3, we can find infinitely many Hamiltonian unstable torus orbits in CHN. Moreover, we give a sufficient condition of the parameter of the Lagrangian torus to be Hamiltonian unstable in CHN. On the other hand, the monotone Lagrangian, that is the pre-image of the product torus of the same radius, is Hamiltonian stable and rigid in CHN for any dimension and the radius R. And as a result on the Hamiltonian volume minimizing problem, we proved that if n is greater than or equal to 3, then almost all Lagrangian torus orbits are not Hamiltonian volume minimizing in CHN, as well as the case of CN and CPN. Drawing the main result in the orbit space of the torus action when n equal to 3, we obtain the following picture. Precisely, the orbit space of the torus action is given by the first quadrant, the three-dimensional Euclidean space when n equal to 3. I parameterize the orbit space by the square of radius. And if you fix the sum of square of radius, then you get a triangle like this. And this purple region is the region satisfying this inequality. And this inequality is a sufficient condition for Lagrangian torus to be Hamiltonian unstable. For example, some Ri is sufficiently small, or equivalently, the torus is very close to the boundary of the triangle, then it can be Hamiltonian unstable. On the other hand, the torus orbit placed at the barycenter of the triangle is Hamiltonian stable. And in the third main result, I said that almost all Lagrangian torus orbits are not Hamiltonian volume minimizing. Here, almost all means that in the orbit space, the set of such torus orbits becomes an open dense subset. More precisely, in this picture, if the torus is not on this line, then the corresponding Lagrangian torus is never Hamiltonian volume minimizing. I also remarked that in my result, the torus orbit in this gray line, except barycenter, I don't say anything on Hamiltonian stability and the Hamiltonian volume minimized property due to the technical difficulty. Now I will explain an outline of proof. The proof is based on just a computation and estimate of the second variation. However, it is not easy. Indeed, the second variation of the Hamilton minimal Lagrangian sum manifold is given by such a not simple form. It depends on both intrinsic and extrinsic property of the Lagrangian sum manifolds. We remark that if L is a minimal sum manifold, then the second variation becomes much simpler form. And moreover, if M is scalar Einstein manifold, then we can easily see that the Hamiltonian stability is equivalent to the condition of the first eigenvalue of the Laplacian. This criterion is very useful if L is minimal sum manifold. However, in our case, any compact sum manifold in CHN is never minimal. So we have to deal with the second variation formula directly. Therefore, the problem is much difficult than the minimal case. If M is a complex hyperbolic space of the second curvature -4, then the Hamiltonian stability of L is equivalent to this inequality holds for any smooth function on L. We shall investigate this by harmonic analysis on L. However, we need information of both intrinsic and extrinsic quantities of L with respect to the hyperbolic metric on CHN. So the first problem is how to get such information. Of course, if you consider an explicit example of Lagrangian sum manifold, you may get necessary information by direct computation. However, I avoid the direct computation here. Instead, I use the geometric similarity between CHN and CN. As I mentioned in the first video, CHN is close to CN. Indeed, the quotient is completely the same. So we try to analyze the second variation for the Lagrangian embedding into CHN through the Lagrangian embedding into CN. More precisely, by comparing the Lagrangian embedding into CHN with the corresponding Lagrangian embedding into CN, we can rewrite the second variation in terms of the geometry of the corresponding Lagrangian. Namely, we have the following theorem. Let phi be a S1 invariant Hamilton minimal Lagrangian embedding into CHN, whose image is contained in the geodesic hypersphere of geodesic radius R. Then this map is Hamilton stable in CHN if and only if the corresponding Lagrangian embedding phi 2, this is a Lagrange embedding into Cn, satisfies that this quantity is non-negative for any function u on R. This formula seems much complicated than the previous formula. However, an advantage of this formula is that all the quantities appeared in this formula are described by the geometry of phi 2, which is a Lagrange embedding into Cn. So we do not need to use the hypergeometric. Also, we remarked that in CHN, the geodesic hypersphere of different radii are not homoscedastic to each other. So the second variation depends on the geodesic radius. And this formula can be applied to not only torus orbit, but also any compact homogeneous Lagrangian in CHN, because any compact homogeneous Lagrangian is S1 invariant Hamilton minimal Lagrangian sum-manifold. Now I apply the previous theorem to the Lagrangian torus orbit in CHN. In this case, the corresponding Lagrangian is a product torus. So we can easily get geometric data of the corresponding Lagrangian. For example, the induced metric is flat, and also we can easily compute the second fundamental form and the mean curvature of the product torus. Moreover, an L2 orthogonal basis of the smooth function of the flat torus is explicitly given by these functions, where M is an n-dimensional vector consisting of non-zero integers. Now we complete necessary information to investigate the second variation, because that our problem is to estimate the second variation of this form. And substituting the L2 orthogonal basis to the previous formula, we can see that the problem is reduced to the estimate of a polynomial of degree 4 with respect to M. Namely, the Lagrangian torus is Hamilton stable in CHN if and only if this polynomial is non-negative for any M. The estimate of the polynomial is not easy, actually. However, we can prove that if n is smaller than or equal to 2, this polynomial is non-negative for any cases. So every Lagrangian torus orbit is Hamilton stable in CHN. On the other hand, if n is greater than or equal to 3, we can find some function so that the second variation is negative for some Lagrangian torus. More precisely, if we take this function, then the second variation with respect to this function is negative if and only if this inequality holds for some triple Ri, Rj, Rk. And this inequality is exactly the inequality I mentioned in the slide of main result. Therefore, there are infinitely many Hamiltonian unstable Lagrangian torus in CHN. In contrast to this fact, we can prove the monotone Lagrangian torus is always Hamiltonian stable in CHN. Also, we can prove the rigidity of the above Hamiltonian stable Lagrangian torus However, I will omit the details here. Finally, I remark on the Hamiltonian volume minimizing property of Lagrangian torus orbit in CHN. When n is greater than or equal to 3, there are infinitely many H unstable torus orbits in CHN. In particular, they are never HVM. Moreover, we can see that almost all Lagrangian torus orbits are not Hamiltonian volume minimizing in CHN by a parallel argument due to Ide and Ono. First, I record the result by Ide and Ono in the case when complex Euclidean space. Suppose n is greater than or equal to 3, and let us consider the standard torus in CN. They show that if there exists at least 3 distinct radius in the product torus, then the torus is not Hamiltonian volume minimizing in CN. We remark that the set that's one this condition is open dense in the orbit space of the torus action. So in this sense, almost all Lagrangian torus orbits are not Hamiltonian volume minimizing in CN. Also, we remark that they proved a similar result for CPN. This proposition is an immediate consequence of the result of Chekhov. That is, the Chekhov gave a necessary and sufficient condition for which 2 Lagrangian standard torus is Hamiltonian isotopic to each other in CN. And the condition is completely described by the data of the radius of the standard torus. Since there exists a simple morphism between CHN and CN, we can apply the result of Chekhov to CHN as map phi. Moreover, we can compute the volume of the torus with respect to the hypergrammetric, and it is exactly given by this formula. Using this result, we can obtain the same conclusion, namely, if there exists at least 3 distinct radius in the original torus, we can find another torus which is Hamiltonian isotopic to the original torus, but satisfied that the volume is smaller than the volume of the original torus. As a summary, we prove the following proposition. Suppose n is greater than or equal to 3. If either this inequality or this inequality holds, then the Lagrangian torus is not Hamiltonian volume minimizing in CHN. Combining with the result of Ide Ono, we summarize the result as follows. Suppose n is greater than or equal to 3. Then almost all Lagrangian torus orbits in CN, CPN, and CHN are not Hamiltonian volume minimizing. However, it is still an open problem whether the following interesting cases are HVM or not. First one is the Clifford torus. This is the standard torus with the same radius in CN, or its quotient in CPN, or its play image by the simple morphism in CHN. Also, it is interesting that the case when n equal to 2. Until now, we do not have any results on HVM property for the case when n equal to 2. Okay, now I stop here. Thank you for watching.